Pluto forces them to ascend and descend as its orbit crosses the path of another planet at the far reaches of our local planetary system. Pluto, the perplexing little planet, is generating a lot of excitement in the field of space science. Recent developments suggest that Pluto could potentially collide with Neptune, causing unease among astronomers and space enthusiasts. Well-known figures like Neil deGrasse Tyson and Michio Kaku have raised alarms about the possible consequences of this celestial encounter. But how did Pluto end up on a collision course with its neighboring planet? Furthermore, what could this cosmic clash imply for life on Earth? Join us as we explore how Pluto's orbit is intersecting with Neptune and why this anomaly is leaving scientists concerned. Once considered a clear planet, Pluto underwent a reclassification and is now referred to as a dwarf planet due to its atypical orbit. Despite this demotion, Pluto continues to captivate and intrigue the astronomical community. Recently, concerns have been raised by esteemed scientists such as Neil deGrasse Tyson and Michio Kaku regarding Pluto's path, which may bring it into closer proximity with Neptune. This alignment suggests a series of potential interactions between these two majestic celestial bodies, with significant implications for Earth. Pluto's orbit around the Sun is unique, setting it apart within our solar system. Its orbit is notably elongated, crossing great distances as it travels. Since its discovery in 1930, Pluto has yet to complete a full revolution around the Sun, which adds to its mystique. Unlike the more circular orbits of the major planets, Pluto's orbit is unusually stretched, making it a distinctive feature in our solar neighborhood. The tilt of Pluto's orbit is another fascinating aspect, deviating 17 degrees from the ecliptic plane, giving it a sharper angle than the orbits of other planets. This combination of its inclination and elongated orbit adds layers of complexity to Pluto's movement around the Sun. One particularly intriguing characteristic is its periodic interaction with Neptune's orbit. For around 20 years in each cycle, Pluto's orbit takes it closer to the Sun than Neptune's, defying expectations given the separate locations of these two planets. Notably, Pluto's orbit is not circular but oval-shaped, leading to significant fluctuations in its distance from the Sun. At its closest approach, Pluto reaches about 30 astronomical units, AU, from the Sun, while at its farthest point, it stretches out to over 49 Australian dollars, double the distance of Neptune from the Sun. Furthermore, Pluto's orbit is tilted at a critical angle relative to the major planets, contributing to the intricacy of its path and interactions with other celestial bodies, particularly Neptune. When Pluto and Neptune do meet in their orbits, their gravitational forces alter their trajectories over time. This complicated relationship highlights the interconnectedness of celestial bodies, with each object exerting gravitational influence over the others, shaping their orbits. In recent years, advancements in observational technology have enabled astronomers to track Pluto's path with remarkable precision, offering deeper insights into its orbit and potential impact on the stability of the outer solar system. While a direct collision between Pluto and Neptune remains unlikely, the possibility cannot be completely ruled out, prompting increased interest and scrutiny from the astronomical community. Despite its small size and distant location, Pluto continues to command attention. So why hasn't a collision occurred between Pluto and Neptune? The answer lies in the gravitational interactions between planets. As soon as astronomers began studying Pluto's orbit, they were baffled by its strange behavior. Unlike most planets, which maintain a consistent plane as they orbit the Sun, the ecliptic plane, Pluto's path deviates sharply, creating an additional layer of mystery. The real puzzle arose when scientists realized that Pluto's orbit intersects with Neptune's path. Yet despite this unusual overlap, Pluto's orbit remains stable, which speaks to the complex mechanics of space. Understanding how celestial bodies like Pluto, Neptune, and the Sun interact gravitationally is a significant challenge for astronomers. Predicting the movement of these bodies is akin to determining where they will be based on their starting positions and the forces they exert on one another. For Pluto, the interaction between its orbit, Neptune's orbit, and the Sun's gravitational pull creates a delicate and coordinated system that allows Pluto's path to remain predictable. Terms such as precession, libration, and the VSOP variations help researchers navigate these complex dynamics. Understanding these principles is vital for maintaining the stability of planetary orbits. When Pluto crosses Neptune's path, it is still about 90 degrees away, preventing a direct collision. The phenomenon of libration ensures that Pluto remains safely out of Neptune's path, even when it approaches. The VSOP variations, named after the researchers von Zeipel, Pacer, and others, explain why Pluto's orbit may seem irregular but remains predictable over time. Despite the apparent chaos of space, certain patterns and rules help keep objects in orbit. These principles work to stabilize Pluto's orbit, mitigating the risk of a collision with Neptune. The chance of orbital chaos highlights how sensitive a celestial body's orbit is to its starting conditions. Even small changes in a planet's position or velocity can lead to major shifts in its path over time. Using complex computational simulations, astronomers can model Pluto's movement in space, observing how slight adjustments in variables can dramatically alter its orbit. In the late 20th century, these simulations revealed that Pluto's orbit, while seemingly stable, can be subject to chaotic fluctuations. Even minor differences in Pluto's initial position or speed can lead to significant changes over long periods. Nevertheless, Pluto's orbit has remained largely stable over billions of years, suggesting that despite its apparent turbulence, its movement follows a discernible pattern. However, predicting the behavior of planets with such eccentric orbits is a difficult task. These systems are so unpredictable that long-term forecasting becomes a challenge. Simulations are useful in estimating possible outcomes, but they also demonstrate the inherent unpredictability of these celestial movements. Gaining a better understanding of Pluto's orbit is essential, especially when considering whether a collision with Neptune could happen in the future. This knowledge helps us understand how our solar system functions and reminds us that even seemingly unstable orbits can be stabilized by gravity and the broader dynamics of space. Exploring space uncovers many surprises, and Pluto's orbit serves as a prime example of such oddities. Unlike the orbits of other planets, Pluto's path around the Sun is more oval-shaped, which means it is not a perfect circle. At times, Pluto even ventures closer to the Sun than Neptune does. This creates interesting dynamics, especially since Neptune is also moving along its own path. While the chance of Pluto and Neptune colliding remains low, it's essential to recognize the forces at play. Gravitational pull acts like an invisible force, keeping the planets in their orbits. So although Pluto and Neptune might appear to be on a collision course, their paths are meticulously shaped by gravity. Studying Pluto's orbit provides valuable insights into the delicate balance of forces that govern space. What might initially seem chaotic is often the result of a finely tuned system of gravitational interactions. Ongoing research and observation are crucial for expanding our knowledge of space, particularly in relation to our solar system. Imagine the implications of a collision between Pluto and Neptune. It would be a groundbreaking event, upending our understanding of the outer solar system. Although we've made progress in our space exploration efforts, such an occurrence would underscore the vast gaps in our knowledge, signaling the need for further investigation. By focusing on how larger planets affect Pluto's orbit, scientists can uncover vital information about the movements of the entire solar system. It reveals that the positions and movements of planets can influence the paths of other objects in space. Despite the complexities of the cosmos, the possibility of Pluto colliding with Neptune remains a concern for astronomers. This raises the question, why could such a collision happen even though it seems improbable? Neil deGrasse Tyson, a prominent astrophysicist, has shared his thoughts on Pluto's reclassification. He believes renaming Pluto as a dwarf planet, instead of a major planet like Earth, is a step forward in our understanding of space. Tyson argues that we are continually learning about how objects move through space, and Pluto's unusual trajectory is a clear indication that there's much more to discover. He finds the mysteries of space fascinating and believes that events like Pluto's renaming engage the public in the pursuit of space science. Tyson works alongside other researchers to warn about the potential risks of Pluto's orbit, especially its potential collision with Neptune. Tyson suggests that such an impact would be a monumental event for the entire solar system, with consequences that could ripple across the cosmos. A collision between Pluto and Neptune would release massive amounts of energy, and could cause Pluto to break apart, sending fragments hurtling through space, potentially colliding with other celestial bodies. Even Neptune would be affected, with its trajectory altered as a result of the impact. Michio Kaku, a well-known theoretical physicist, offers his own perspective on the relationship between celestial mechanics and space exploration. Kaku emphasizes that studying Pluto's orbit can provide critical insights into the future of space exploration. He believes that understanding the intricate gravitational interactions between celestial bodies like Pluto can improve future missions, helping us navigate the solar system more safely and predict potential hazards. Kaku's work in theoretical physics, particularly in string theory, aims to decode the fundamental laws governing the universe. He suggests that by studying the dynamics of celestial bodies like Pluto, we can unlock deeper understanding about the forces that shape our reality. Both Tyson and Kaku agree that observing events like a potential Pluto-Neptune collision offers an exciting opportunity to learn more about the universe. In particular, such an event could have profound implications for our understanding of string theory. String theory seeks to explain the fundamental forces of nature by modeling the universe as a series of one-dimensional strings. A Pluto-Neptune collision could generate extreme conditions that would provide valuable data for testing string theory predictions about spacetime. While the immediate impact on Earth would be negligible due to our distance from the solar system, the scientific knowledge gained from such an event could be transformative. It would expand our understanding of the fundamental nature of the universe, pushing the boundaries of theoretical physics and space science. As researchers continue to study the gravitational influences of neighboring planets like Neptune, the dynamic and ever-changing nature of space becomes increasingly evident. However, space remains full of mysteries. The three-body problem, where multiple celestial bodies exert gravitational influences on each other, is just one of the many complexities that scientists are working to solve. The ongoing exploration of space is crucial for broadening our understanding of the universe and the principles that govern it. Although the likelihood of planetary collisions is extremely low, the possibility still exists due to the influence of gravitational forces. These forces can alter the orbits of planets, potentially leading to collisions over time. One example of this phenomenon is the TRAPPIST-1 system, which contains 7 Earth-sized planets. The gravitational forces between these planets can create orbital resonances, making their orbits less stable and potentially leading to collisions in the future. Researchers are closely monitoring these systems to better understand how celestial bodies interact and how planetary paths can shift. In addition to planetary interactions, rogue planets, planets that no longer orbit a star, can drift through space. These planets, which were once part of a star system, can travel vast distances and occasionally collide with other star systems. However, the vast emptiness of space means that the chance of a rogue planet colliding with another planet is low. Despite their rarity, rogue planets are intriguing objects of study for astronomers. Finally, when galaxies collide, the gravitational forces involved can alter the movement of stars and planets. While planets may not collide directly, their orbits can be disrupted, potentially flinging them out into space or causing them to collide with other planets or their host stars. This disturbance can lead to the creation of new celestial bodies or even the birth of new stars. The late heavy bombardment theory suggests that around 4 billion years ago, an increase in impacts from comets and asteroids occurred, likely caused by the movement of the outer planets like Jupiter and Saturn. These impacts disrupted the orbits of smaller objects in space, many of which were ejected into the inner solar system. Although these impacts did not involve direct planetary collisions, they serve as a reminder of the power of gravity to reshape the paths of objects in space. The late heavy bombardment theory is a fascinating concept that suggests the early solar system was subject to intense cosmic bombardment. During this period, the outer planets, such as Jupiter and Saturn, were believed to have undergone substantial movements, displacing many smaller objects and throwing them onto erratic trajectories. As a result, these objects collided with the inner planets, leading to significant impacts. While these encounters didn't involve direct planetary collisions, they had a lasting influence on the surfaces and compositions of the planets, particularly Earth. It's even believed that this bombardment may have played a role in bringing essential elements, such as water and organic molecules, to our planet, contributing to the conditions necessary for life. These impacts, which occurred billions of years ago, are a stark reminder of how gravitational forces from larger bodies can disrupt the movement of smaller celestial objects, altering their orbits and trajectories. In this case, the powerful gravitational influences of Jupiter and Saturn were instrumental in shaping the course of many objects that ultimately found their way into the inner part of the solar system, further complicating the delicate balance of forces at play in our cosmic neighborhood. The effects of these early cosmic collisions can still be seen today in the craters found on the surfaces of planets, moons, and asteroids. Such events underscore the complexity of space and the fragility of planetary orbits. Just as Pluto's eccentric orbit raises concerns about the possibility of a future encounter with Neptune, the larger historical impacts of cosmic forces help scientists understand how planetary systems evolve over time. The notion of celestial bodies colliding or influencing each other's paths serves as a reminder of the dynamic nature of space and the potential consequences these interactions may have on life within our solar system and beyond. The delicate interplay of gravitational forces is further exemplified by the concept of the three-body problem, a classical dilemma in physics and astronomy that describes the difficulty in predicting the motion of three celestial bodies that influence each other gravitationally. As we observe the relationships between planets like Pluto, Neptune, and others in our solar system, we are reminded of how challenging it is to predict long-term orbital paths with certainty. Despite the advances in computational simulations and observational technology, the precise movements of these bodies remain elusive, especially when considering how even tiny variations in speed or position can have profound effects over long periods. Additionally, researchers remain vigilant about the potential risks posed by rogue planets, celestial bodies that no longer orbit a star and instead drift through interstellar space. These planets, ejected from their original solar systems due to gravitational perturbations or close encounters with other stars, present a unique challenge to our understanding of planetary dynamics. While they are rare, their presence in the cosmos highlights the unpredictable nature of space over time. Rogue planets can travel vast distances, sometimes approaching other star systems, but the vast emptiness of space makes direct collisions with other planets or stars highly unlikely.